Thank you, folks. Thanks for coming to the talk. I know it's getting kind of late in the afternoon. I hope everyone's had a really nice DevOps Pro today. My name is Will Foster. I work for Red Hat in Ireland. I'm part of kind of a two-man DevOps team that works around performance and scale engineering. So our focus is pushing all of the Red Hat open source products as well as upstream things like Docker and Kubernetes and OpenShift, and I don't even know how many products we have, making sure that they perform at scale and that they have acceptable performance for customers and consumers. So my talk today is going to be on QUADS. So QUADS is an in-house automation framework. It's basically a loose collection of tools that we've developed to solve some of the problems that we've had managing a very large infrastructure with very few people. So before I sort of jump into what QUADS is, I think it'll help you to understand exactly what I do at Red Hat. And I like to use a car analogy because no one's ever used a car analogy before on the internet for technology. It's never been done. No one's ever used a car analogy, ever. So I'm going to be the first one in history to ever do it. If you think of like a racetrack and race cars and high performance racing, like Formula One or any of the sort of crazy things that happen when cars go around in circles multiple times and one person tries to win. So high performance computer servers, think of these as race cars. And think of the race tracks as high performance networks. 40 gig, 100 gig networking, top of the line, maximum throughput. And think of the races, the individual races that happen with these cars on these race tracks as product performance and scale testing. The race car drivers are the scale engineers. They are the ones who are going to write code. They're going to patch things. They're going to improve scalability and performance of things like the Linux kernel or any subset of, OpenStack, for example. You could name any product. That's kind of their job. And myself and my colleague, we are sort of like the pit crew. We're the enablers of all of these races going on all the time. And our job at Red Hat is to coordinate and manage as many concurrent races happening as efficiently as possible all the time. So if I lost you on that analogy, there's a very simple sort of breakdown. This is the Reader's Digest version, which is basically there's two of us. We manage about 300 to 400 high-performance bare metal machines, a bunch of network switches, a large infrastructure. And this environment is constantly in a space of spinning up and spinning down, being sliced and diced, handed out in sections to different engineering groups within the company, and then reclaimed. And we've automated our jobs with Python, and instead of doing sort of the manual tasks that go along with administrating network architecture, doing systems engineering, we just work on the automation and the tooling to do it for us. So, no DevOps conference is free of some sort of modicum of how do we DevOps. So I'm going to save you kind of going through the details here because the other speakers today have probably done a better job than I'm going to do as far as explaining DevOps principles and how you adapt it to your organization. This talk isn't about that. I'm just going to explain to you how we've used some of the DevOps methodology and developed our own tooling to make the whole production lifecycle of software engineering a lot easier on everybody. There's two of us. We have a team of about 160 to 180 what we would call performance engineers. And we embed ourselves in all of those teams. We participate in their scrums, their meetups. We become very intimately familiar with their code base. Sometimes we write patches to help some of the products, but most of the time we don't. But we create a very tight-knit relationship with core engineering and core development that we can anticipate what their needs are from a development end, either when they need it or usually before they need it. And everyone's just happier because of that. We've also instituted basically a team rotation where we will pick one core engineer and they will join our DevOps team for about a 2-month period, and then they'll cycle back into the regular kind of developer pool. So that's been awesome. All of our code and tools are open source. QUADS is open source. It's on GitHub. Really, we also focus on transparency, on making sure that people know what we're working on, that there's no silos within the organization. And we strive very strongly to document everything. Now, part of QUADS is going to be automating your documentation so you don't have to do it. We'll get to that in a second. But basically, we just try to be excellent to each other. You know, we just give everyone the benefit of the doubt. So, let's talk about QUADS. What it is and what it isn't. QUADS is not an installer. It's not a provisioning system. It is a loose collection of tools that achieve a full life cycle of deploying infrastructure for people. QUADS takes care of some of the boring stuff that we would probably screw up, like documentation or systems administration or network administration, where it's fun to do it once, but it just really sucks to do that all day. So it pretty much automates the things that we either don't want to do or we're probably going to mess up. Kind of the core ethos behind it is that we don't want to build systems and build systems and build systems. We want to build one system, and then we want to have that system build and automate and orchestrate all the other systems for us automatically. So how do we do this? The approach is pretty simplistic. We keep basically a YAML structure, a YAML data set that describes metadata about our entire infrastructure, about our servers, about our switches, about where in a point in time they're supposed to be living and what they're supposed to be doing in that exact point in time. And we drive all of our automation around this sort of schedule-driven methodology. With this comes things like automating all of your documentation or providing up-to-date visualizations on exactly what your hardware and what your data center is doing at any point in time. A little more detail, you know, a lot of this is kind of fluff. I'm not a marketing person, so I'm not going to say something like auto healing. You know, there's no such thing as auto healing, right? Nothing is Wolverine, okay? Like if a DIMM goes bad in a motherboard, that memory doesn't heal itself, okay? So I'm going to explain to you exactly how we do it, and I'm going to show you how you can adopt some or all or even just the ideas here and maybe apply it to your infrastructure where you work. So QUADS creates and manages a date, time-based YAML schedule for every asset that you own. It drives all the system and provisioning and network provisioning from that schedule. If you happen to be doing OpenStack, it will generate what's called the instack-inf JSON file, which is kind of a helper file to help deploy OpenStack. And it automates all of your documentation for you. So how are we using it? So we talked about this Scale Lab that we run, this large bare metal environment. The Red Hat Scale Lab is 300, 400 bare metal servers where we test and vet all of our products at scale. And we support around currently 25 or 30 parallel workloads that are running 24/7 all the time. This is mainly written in Python. There's a little bit of Ruby and a little bit of Shell in there. But it's fairly simplistic. I'm not a developer by trade. I'm just a sysadmin who is lazy and wants to automate everything so he doesn't have to do it manually, which is, I think, a good place to be in the industry. So I want to show you a physical representation of what QUADS achieves. And everyone likes graphs. Everyone likes pictures. So this is an example of the Scale Lab, sort of the itinerary earlier this year from February onward. What I want you to glean from this is that we see different workloads sort of carved out. Each one of these kind of isolated workloads are what we call clouds because we're not very creative and we just want to continue to pile on the ambiguity of the word cloud. Everyone knows cloud just means someone else's computer. So this is someone else's computer from the perspective of people that are using the hardware. So what you want to take away from this is that all of these sort of sliced and diced assignments have a very specific development purpose. We see the list of machines that are involved. There's metadata such as maybe the ticket requests that instantiated this thing from being put in place. And this entire scheduling starts at any time in the present and can go out as far as you want in the future. So you can schedule things in the future. It's kind of like a fake time machine. So all of these assignments have been scheduled automatically. They've spun up by themselves at the appropriate time when they were scheduled. All the validations happening, all of the automated configuration of the network ports, the user accounts on the IPMI or out-of-band interfaces, foreman logins so users can self-service provision. All this has been done by QUADS, and it's done automatically, and this is sort of the end result of what you see. Here's kind of a more recent example. Again, sort of the same thing. The theme here is that bare metal servers are expensive. Even rented resources like an Amazon or Azure or any sort of cloud provider is expensive, especially if you're not maximizing your usage of it. So one of the main drivers behind QUADS is efficiency in using your hardware all the time and getting the most out of your CPU cycles. So what we try to achieve here is to tightly group scheduling of as many resources as possible to happen simultaneously. Here's an example of a workload that we've done a couple months back. This is just a random storage workload that I happened to pick. It's a Ceph workload. It's some IOPS here. It's kind of, this means something, I don't know. Draw your own conclusions. It's just an example. So you're probably thinking, and I get these questions a lot, is well, what problem are you solving here? Why would you go and make your own sort of scheduler orchestrator when there's tons of stuff on the internet that does something similar? And that's what I'm going to explain to you right now. So what are the problems are we solving here? The main one is server hugging. So has anyone heard the term server hugging? So when I explain it, you'll be like, oh, yeah, server hugging. Yeah, I know what you mean. So server hugging is the idea that when you give someone something, particularly in IT, when you give someone, a developer, a server or a set of servers, it's not theirs. It belongs to the company or it belongs to maybe their development group. But they have a tendency, we have a human tendency to hold on to it as long as possible, to not let go. This is ours. This is, you can't have it. No, I'm busy. No, it's not yours. And we call this server hugging. So one of the things we wanted to eliminate is the idea of server hugging, or at least cut down on it. There's always going to be more demand for hardware and resources than there are actual resources. So being very efficient with how we do this is at the key. Now you can't take something away from someone and not give them something back. That's just kind of a jerk move. You don't want to just be the taker. What we give back is increased transparency. There is no question if there's hardware available. Everyone can see what the servers are doing at any point in time. And everyone can see what all the other people are doing with the servers. So we take away the server aspect, the server hugging aspect, but we provide transparency instead. And that's what the tooling does for us. And the technical way that we solve this problem is by having clearly defined scheduling for servers and for assignments. And we can publish the future schedules in advance so people know when to plan their development cycles around it. In an ideal world, you would know the development schedules of all of your products in your company. And those product managers and those engineers would be in constant contact with you and tell you, okay, in March we have this beta release is going to come out. We need some hardware to test the scalability. In reality, none of this ever happens. Okay, schedules slip, people forget, there's blockers. Any sort of level of chaos is going to be introduced, right? That's Murphy's Law. So what you can do is try to plan around those sort of things happening by sticking to scheduled guidelines. So another thing that we're trying to solve, and this is huge, I think everyone can relate to this, is we want to eliminate human error. There are certain things that I know I'm going to screw up if I'm doing them manually. I'm on a switch and I'm doing a VLAN, or I'm removing a port or adding a port. Eventually, sometime I'm going to screw that up, and someone's whole set of machines is going to go offline. Plus, that stuff isn't very fun to do day in and day out. So part of this automation is we want to relinquish ourselves of as much human error as possible by basically letting the automation do it for us. It's going to do it better than us, and if it doesn't, then at least it's funny when it all fails. Because when automation fails, it usually does it in a glorious way. It's usually not just a machine or two. You know, your automation is so tuned towards going in and doing a particular task. You know, you make a configuration management mistake, it somehow passes through your environment, it goes all the way out to production, and now your entire fleet goes offline. You know, we've seen this happen in the last year with nameless companies. One operator mistake in the config management side, they're offline. You know, it's happened to Amazon, it's happened to everybody. So that's kind of the double-edged sword of automation. But generally speaking, machines are going to do a better job than you are as an operator. Another thing that we want to solve, we want to be more like Airbnb and less like a hobo house. So Airbnb has very clearly defined guidelines. You generally get what you see, not all the time, but it's generally there. They have strict requirements. You can only have an Airbnb for 4 weeks at a time, no longer. And for the most part, things are uniform. You would expect that the place is livable. You would expect that it's a little more cozy than, say, a hotel room. Maybe not all the time, but most of the time. So we want to be more like Airbnb with our bare metal environments and less like a hobo house where anything goes. There's more uniformity there. And really kind of the last thing we want to solve here is time and resources. So I've done some back of the envelope math around what it would take if one person was to, say, provision 100 machines, all of their corresponding networks and VLANs, all the user account stuff, all the role-based access manually. I'll show you how I got to this number, but basically it would take about 90 hours of work to hand over a whole environment, an isolated environment of 100 machines to somebody. You know, if you had a 12-person team, you could maybe do it in a day. We are able to do this with QUADS in about 2 or 3 hours on a Sunday. So we don't, usually nothing's happening on a Sunday. It's usually not a work day for us. So that's when our automation fires off. We're not in a hurry. We're not Facebook. We don't need to have it in 2 minutes. So 2 hours is okay for us to have a whole fleet provision. This is how I got to that number. I'm kind of using some conservative estimates here, but we say switch port reconfiguration, 2 minutes per port, 4 ports per server, so on and so forth. Basically everything QUADS does, but if you were to sit down and do it manually. And God help you if you, in 2017, do this manually every time before you give a server out to somebody in your company. All right, so let's look at some architecture. So I explained what QUADS does. I've explained how we use it, why we created it. And I want to show you now kind of how the architecture looks. So this is maybe the ugliest diagram you're going to see today. It's not going to win any website awards, but it's kind of colorful, and I wanted to keep it simplistic. So who here has seen the movie Office Space? Which also I've decorated my laptop here with the bobs. If you haven't seen Office Space, go see it. It's a great movie. It's about a horrible office environment that you don't want to work in. But the guy in the middle here is Milton, and we're going to use him as kind of your regular operator, your regular DevOps guy. And the way he interacts with QUADS is through an HTTP API. There is a daemon service, and then there's a CLI client. It basically makes API calls to the daemon. The daemon manipulates a YAML schedule, which holds key value pairs describing the environment, the switching, the ownership attributes of the environment. And this maintains sort of the when, the where and the when of the environment. Foreman, which we would call kind of our provisioning backend or our inventory backend. You don't have to use Foreman. I'm a big fan of Foreman. You could probably supplant this with, say, Ansible Facts, for example. But in this case, we're going to talk about Foreman. So Foreman actually does the reprovisioning of the servers for us. And then there is a hook into QUADS called move hosts, which is open and modular. You can define move host as what your provisioning workflow would be. It could link to a script. It could link to, you know, an application call, an API, a post, whatever. And then basically your machine's provision. There's changes that happen to the IPMI interfaces. There's automation that happens to the switches where the ports are reconfigured depending on the VLAN design that you want. And then it goes through validation and you get your hosts. So the main consumable here are two things. You have a auto-generated Wiki environment auto-generated visualizations, and you have your actual physical host. Now there's ancillary services we plug in, like Nagios. We have an Elasticsearch plugin that pulls statistics and makes graphs and things like that, but it's not part of the core part of QUADS. So, when I talked about the move host, this is kind of an open-ended command that you define yourself. We don't want to make any assumptions about your environment. We put things together in a very modular fashion that you can pick and choose the components that you want to use. So when it is time for a host to actually reprovision or a set of hosts into what we call a cloud, this is what happens on the back end on the foreman side. There's some role-based access stuff that changes. The IPMI interfaces are reconfigured. The operating system is provisioned. There's some post-automation that happens. And then there's a validation phase. We gate on 3 sets of validation checks. There's a network validation that ensures that the VLAN configuration is correct on the switch side. There's kind of an F-ping that goes out to make sure that the backend interfaces can communicate. And then there is a systems provisioning that makes sure that every operating system reprovision is successful. And lastly, we make sure we can pull metrics off of those hosts to populate some of the visualizations. When all of these validations have passed, we send out an IRC notification and an email to the user saying, hey, you just got 500 machines, you have them from these dates, here's links to the documentation, have fun. So again, this is sort of the programmatic back end of QUADS. So for every host, it has an entry in this YAML schedule. So what happened here when the certain time and day happened, at 2200 on a certain day, QUADS knows it needs to fire off provisioning for a set of machines. It needs to move them from their old assignment or maybe multiple assignments and put them into the current one that it's supposed to be in. And all of that intelligence is in the YAML structure per host. So we can see now number 5 is where this host is going to live until December 6th at 2200. And it's going to participate in this Cloud 02. And that and many of its other hosts like it are going to be in the same sort of environment. It's going to have its own isolated network design, and people can get their work done. I want to talk a little bit about the network design because I've given a similar talk about QUADS and automation, and I never got into the network stuff. And I always had questions about that. So we support 2 types of VLAN designs. There's basically the default mode, where if you have 5 hosts, the first interface on all those 5 hosts are all in the same VLAN. The second interface on all those hosts are in another VLAN. The third interface, and so on. That's kind of our default mode. We also have another design where all the interfaces are all in the same VLAN together. And this is open-ended. As we get more demand to support more VLAN architectures, we're going to build that out. We have an RFE in now to do LACP bonding and lag, so that's in progress here. This is a diagram of kind of all the hardware, the hardware types that we have in our lab. So in a perfect world, you would probably have a homogeneous environment. You would be lucky enough to have the funding to have all of one type of server. Generally speaking, it makes things much easier if all the hardware is the same. But in reality, not many people have that benefit. So we are heterogeneous between currently 2 vendors, Dell and Supermicro, and then there's a few different models between these. But what I want to illustrate here is that we typically will have 4 what we would call internal 10 gig or 40 gig interfaces, and then we would have 1 external, what we call the public network, where the provisioning happens. And all of this VLAN design and shuffling and things that happen when assignments go out, that physical isolation happens on these first 4 interfaces. That public network is always left alone. Cool. So who likes documentation? Who likes to write documentation? Exactly, nobody, right? Documentation is one of these things that is always lacking with the product. Especially open source projects are especially bad at up-to-date documentation. It's just not, I know very few people that like to do it. It is also an area that can be disastrous if something goes wrong, if you have incorrect documentation, because every decision that is made based on that documentation is going to be incorrect. So we automate all the documentation and all the visualizations by a very simple construct. We basically query our two sources of information. We query Foreman, which is sort of this central inventory point that the servers are provisioned out of. It controls the DNS. It knows about certain bare metal aspects of the hardware. And we query QUADS because it knows where the hardware is supposed to be and who owns it. We munge that information together into Markdown, and then we use a Python API to push it up to a Wiki page. And then this gets updated every minute. Now, you don't have to use WordPress. We're using WordPress. You could use MediaWiki. You could use anything that supports a reasonable API that you could automate this sort of stuff. So this is what the documentation looks like. This would be kind of your typical racks wiki, which would break down per rack where your servers are located. Certain sort of static information that's not going to change that often, like IP address or MAC address. But one thing that is going to be static, or that is going to be dynamic, is on the far right you have workload and you have owner. So that is updated depending on who's actually using the machine. Drilling down more into that, this is sort of a summary view of all the concurrent clouds or assignments that are running right now and managed by QUADS. And we have a couple of other dynamic sources that are generated as well. If you drill down into the individual assignment, you can see kind of some other information that we thought is pertinent. We can tag faulty systems. So if there's something wrong with the hardware, we can just add a key value pair of faulty. It removes itself from the provisioning pool, and it puts it into the check this machine pool for the people that are physically on the location where the hardware lives. We also have some visualizations. Now, this calendar view we don't really use it that often, but it publishes a per month breakdown of what's happening in the environment. So if you're an engineer and you might want to see what's happening at any day in the month, you can sort of pop in here and you can see, you can load it in your phone, whatever. This is the one, this heat map visualization is the one that we find the most use of as operators, as folks that are trying to schedule these resources in the future and allocate as many tightly woven sets of parallel workloads as possible. It looks a lot like the Windows 95 defrag utility. If you remember the big blue thing with the blinking dots, it's kind of ugly, but it is efficient. It does work. You can sort of hover over. The top is the days of the month. The left is going to be all your servers, and you can see what those sets of machines are doing, either by color or by texture. So if I was to zoom it out, it would look something like this. Again, this is like 1990s web dev, but it is efficient. I can take one glance at this and I can see, okay, the gray, these are free machines. So I know that Josephine engineer needs to have 30 servers, but between this date and this date, well, I can easily see what's available from this fleet, and then I can schedule it with QUADS. Some other things that we pick up is we do Ansible facts collection. There's a very cool open source project called Ansible CMDB on GitHub that basically runs fact collection against all your machines, and then it populates like a web page or JSON or CSV or whatever. We have this linked off the wiki. And then something else we just put in recently was pulling in some biostats for Dell machines. Because we're focused on performance and scale, so things like CPU profile are important to us. So I want to talk a little bit about CI. We use Garrett and Jenkins. When people submit a patch to QUADS, it goes through a full gamut of CI checks. There's some sort of functional tests that happen where it mock runs all the QUADS commands. There's Flake 8 checks for Python. There's shell check, and then it votes on it. And then once it's reviewed, it gets merged into master. Now, when it gets merged into master, we auto-build an RPM using the Fedora Copper service, which is a cool service, by the way. Anyone can use it. It's free. And it has the ability with webhooks to detect if a change was made in your code repository, and then will automatically pull it in and rebuild an RPM for you. I have a blog post of how to set this up if you're interested at all at hobo.house. I tend to blog about things not hobo-related all the time, usually tech stuff. So I want to talk a little bit about the engineering challenges that we have. So we are using a flat file architecture. We are not using a database. This comes with some positives and some negatives. The positive is pretty obvious. It's easy to debug. The code base is very simple. And it's very easy to sort of replicate a test environment. We ship a tool called QUADS Sandbox that you run it. It instantiates a local QUADS daemon and listener. It creates a bunch of mock hosts for you for development purposes. The downsides of not using a database are fairly obvious. First of all, it just doesn't scale. We are tied to basically sequential operations with the daemon and the CLI. And currently, and this is really purposeful, that we only intend on one person doing the scheduling at any one time. Time is also an issue. When you're doing sequential operations, it takes substantially longer than if you were to do them asynchronously. So it takes us about 2 to 3 hours to deploy 500 to 600 to 700 machines. That's okay. We don't care. It happens on Sunday. But other people may care. Not everyone needs to be Facebook or Google. But you know that 2 or 3 hours can be cut down substantially if we were to use like a proper distributed architecture, which I'll get to. So I want to show a little bit of code samples here, but I'll be really quick because we don't have that much time. This is how we basically, this is dirty sysadmin hacks 101, okay? This is how we read without a database. We basically rely on system calls and we rely on Python locking and threads to make sure that the data, before anything is queried, that in-memory data is flushed to the YAML schedule and all of the flat files match or whatever is in memory or in active use is flushed to disk before we allow queries to happen. We have it set up that there's not that many query operations, but again, this is not going to scale if we want to go to several thousand, several 100,000 machines. We force data integrity as well with this sort of approach. Dirty sysadmin hacks number 2, we write data without a database. We do Python thread locking to ensure data integrity, and we basically grab and hold of locks and ensure that the write is successful, and then we release the locks. Because you're dealing with system calls and it's in a sequential fashion, it's actually pretty fast. It's actually sub-millisecond. But when you are doing a lot of this, you have a lot of machines to provision, you have a cloud of about 1,000 bare metal machines going out, it can take a couple hours, and that is something that we want to address. But you don't need a database. You don't need a database to write data. So we've kind of written these safeguards in some very simple Python to ensure that. So where would we move from here? I think really the ideal way to do this is with an asynchronous design. This is kind of our 2.0 milestone. We're going to have a queuing system. I'm a big fan of Flask and Celery and SQLite, so that'll probably be the foundation of it. But it's going to scale a lot better because if we want to do more, we just add more task processors at the back end. Maybe we throw in another message queue system. Maybe we toss an HA proxy in there, and it can sort of scale horizontally. The current design does not. But again, that was on purpose. But we are slowly hitting that point that maybe it's a good idea to move to a database. So I want to just summarize here. The QUADS methodology, really kind of the reason behind it is that as companies grow past 20 people, you have this tendency of departments to become siloed, and every department buys their own hardware, and there's different hardware, and nothing is consistent. They're bought at different times, so the warranty might expire on a different area. You have this sprawl of infrastructure debt. And your ability as an engineer to get access to high-performance hardware is almost directly based on how political and savvy your manager is to kind of fight with the other managers to get more budget, so then you can collect more, and then you have these little silos of hardware everywhere, and nothing's consistent. So the impetus behind QUADS was, let's not have these little siloed areas of infrastructure. Let's put it all in one bucket, but let's have a programmatic approach to slicing and dicing and leasing out the hardware. And let's publish everything so everyone knows what it's doing all the time. That's kind of the idea. Coming from a strong sysadmin background and generally loving the sort of KISS principles, the keep it simple, stupid principles. We wanted to stick to small little modular tools that do one thing and do one thing well. So we've sort of tried to stick to that. And again, from a sort of a selfish perspective, is that documentation is so important, but I don't like writing it. Connectivity, layer 2, layer 3 stuff, I'm fascinated with it. It makes our current world work how it works, but I don't want to do it day in and day out. These little things that are error prone, we want to automate, and that was also kind of our selfish push to creating quads and to, you know, kind of stringing it all together. So the whole thing is about a year old. There's about 5 active contributors. Everything's open source. It's on GitHub. Use it and abuse it, clone it, send us a patch maybe. Do whatever you like there. So I think we have a minute or two for questions. I did want to point out we have a Red Hat booth over here, so come say hi to these lovely people. You can check out the QUADS source code up here, github.com/redhatperformance/quads. You can find me at hobo.house. And I'm on GitHub as well. I've got a ton of Ansible playbooks that you might like. I have a whole Ansible elk stack that's fairly popular. I have another one for Nagios. So sharing is caring, folks, and thanks for your time. I appreciate it.